All right, let's get started. So we'll pick up with a couple of slides from last time. We kind of weaved in with these. So just a couple of announcements. There's this new Canvas activity that's online if you choose to do it. It's due before lecture C1. So this is lecture B2. There's a B3, and then C1 is, so I guess today's Thursday, so it'll be like a week from today. Homework B1 has been available on Canvas. It's due soon, so I think it's due on Tuesday. So a lot of people have already submitted it or submitted to ask questions about it. There's some discussion topics on Canvas about it. Upload is a Microsoft Word document. Typed and electronically formatted to make it easy to grade. So communication is a component, an AVET component of this course. Simulation is often about communication. If you really want to go for it, you can even consider picking up LaTeX skills instead of Microsoft Word skills, which are something you might use in grad school. But the example that I do online to help with this is kind of showing you how to build a table and do a hand simulation just within Microsoft Word. And I think it's not too bad. So a couple of hints or answers to questions that have come up. So I'm expecting at least 2 examples for each category of the system. So the hint that I gave this last time is if you're having stuck trying to think about, well, what's another type of entity, you're probably thinking maybe a little too general about an entity. So instead of thinking about an animal as an entity type, you could think, well, what if I have dog, cat, bird, and human? So in that case, you might, you might have, an animal might have attributes, and that attribute might be species. But instead of that, I could have just created 4 different types of entities that are just 4 different species that might arrive at different rates and do different things. So, or a little closer to the examples, instead of just passenger, I might have a priority passenger, a business passenger, and an economy passenger. And so that's 3 different types of entities right there. So, and you can also imagine things like, well, if it's an order to a restaurant, you might have a mobile order, you might have a phone order, or you might have somebody who comes in person. And then those different ones you can imagine go through different processes later. So if you're having trouble thinking of different types of entities, then think that, try to break your entity down into subclasses and make those your entity types. The other thing, so when you go to question 2, if you're having trouble figuring out what these things are, LQ, LS, and all that, they all come from table 3.2 in the course textbook. Just as a quick review here, LQ is the number of customers waiting for service in the queue. LS are the number of customers currently being serviced. So LS will always be either 0 or 1 for this example. In B, now these are all cumulative, so they're not state variables because they accumulate information over all of the previous time steps of the simulation. So in D is the number of customers who have departed thus far. S is the sum of the response times to all the customers who have departed thus far. And then F is a special one. That is a number of customers who have departed who spent 5 minutes or more in the system. So F will always be less than ND, but both ND and F will climb over time. That S will climb over time. So none of these will be decreasing. So I'll give some some sanity checks here in a second, and one of those will be that these things are all supposed to be non-decreasing. Now the response time that is referred to in these things, response times right there, is the total time from arrival to departure. So a common mistake is to only add in the service time. But we want to accumulate not only their service time, but how long they waited in the queue. And that's the reason why every entity is stamped with their arrival time, because that way when they depart, you can do a simple calculation to subtract their arrival time from the current time, and you can see how long they've been in the system. And that is their response time. So in question 2, the missing leading into arrival rate it's not a mistake. It's not technically missing. We just sort of presented it in that way, the same way the book presents it, to emphasize that the first customer doesn't have anyone in front of them, so you don't have to wait for them. They only have a service time. But the second customer, you have to wait that inter-arrival time after the first customer arrived before they get there, and then they also have a service time. So that blank spot is just meant to indicate that you're starting right at service of the first customer. You've already kind of waited for them and you've forgotten about that waiting time. Now, another way to look at it is that these are eventually going to be drawn from random variables. They're going to be drawn from distributions. So don't think of them as two lists that are related. Think of them as two independent lists. I have a list of inter-arrival times and I have a list of service times. When I need a new inter-arrival time, I just take the next one off the list. When I need a new service time, I just take the next one off the list. So most of this lecture, the back half of this lecture here, is we're actually going to work the homework example with different numbers, and you'll see how that works. So the hints and sanity checks, the future event list for an MM1 like Q like this one, for one that only has one server and one set of arrivals or one arrival process, you'll always have exactly one arrival in the FEL. So now if I made a mistake, and I don't think I did on this one, and I gave you, too few inter-arrival times, then it's possible you might run out of inter-arrival times. But that's kind of a bug in the specification that I gave you. In general, the FEL should only have one, and exactly one, not less, not more. If you have less than one arrival, then you're not going to be able, your FEL is never going to bring you to another arrival. So you always need to know that the next arrival is coming. But you're not going to have two arrivals because you only schedule an arrival after you're done processing an arrival. So you process arrival, get rid of it, and schedule a new one. So you only ever have one arrival. Similarly, you're not going to have more than one departure event. So you might not have any departure events currently scheduled if you're just sitting there waiting. But you won't have two departure events because you can't schedule a departure until the other customer has departed. So even in your head, you might be able to kind of forward simulate and say, I can tell that customer 1 is going to depart at 15 and customer 2 is going to get right in there and then depart at 19. But don't do that calculation. Let the simulation do that calculation. You just schedule the first departure and let the logic schedule the second when it needs to come up. The clock will always match the time in the first event record from the FEL in the previous line. So we know where we go next by looking at the first event in the previous row. So we'll see that in the example we do today. Other quick spot check things. So when people come to my office and they ask for does this look like I'm doing this right? These are the quick things that I look for. So the number of customers in your checkout line should in total be the sum of LS plus LQ. If it's not, then you've probably updated these incorrectly. And then LS will always be 0 or 1. The cumulative statistics will always be non-decreasing because in this simulation, they're keeping track of, they're either a sum, well in this case they're all three sums, and because they're sums of non-negative values, then they're always non-decreasing. F will always be less than ND because F is a subset. These are all the customers who departed. These are the ones who are unlucky enough to depart with a long response time. So F is always less than ND. And the response time jumps in S will often be larger than the corresponding service time because the response times include that waiting time, not just the service time. So if I were to scan through your list and I look at each one of your jumps in S, like S in the previous line was 10, and the next line it's 12. And I notice that the corresponding service time of whoever departed was 2, then that will tell me that, well, maybe you only added service times, you didn't actually add the whole response time. So remember, response time is time since arrival, not just the service time. And if you do the bonus part in the Excel spreadsheet, and if you really understand the output of that, you should be able to use it to check the previous one because you put in the same arrivals and the same service times into the bonus. And so you should be able to glance through that spreadsheet and be able to say that, oh yeah, look, this customer did depart at this time, just like I thought it did when I did the hand simulation. So you can use the Excel spreadsheet in the bonus as a check to see if you did things right in the hand simulation. Are there questions about the homework? Yeah.
All of this is posted, right?
Yeah, these slides are already online. Other questions? Hope everybody's feeling much better about hand simulation stuff. Eventually we will get into computational simulation with actual software that does all this for you, like Arena. And so you'll do a final project, which you're not going to really worry about until after the midterm. The midterm is scheduled for October 8th. And then after the midterm, that's when you will form groups and start thinking about your final project. And we'll walk through, we've got like a simple assignment where you form your group and you tell me who's in your group, and then there's sort of subsets. So we don't leave you hanging. But one of the things you can do for your final project, you don't have to do this, is actually in your group enter the IISC Rockwell Arena competition, in which case you won't pick a system, you'll just use the system and the data sets that they give you. And so it's usually a little more sophisticated, but it is a simulation competition designed for your peers, designed for people at your stage in your education. And so we highly encourage ASU students to take part in that because we love to have ASU representation, but it's no pressure. And so if you're interested in this, these slides are online. You can take a look at the website here, or you can email Bonnie to ask specific questions. But the basic idea is you have to register, I think, this year by September 30th. And by registering, you just sort of list who's going to be in your team. There is a registration fee of, I think, $30 in the past. I think the IISC student group has offered to pay that. We've also, in SIDC, we've also offered to pay that. If you're interested, I can take it up with the director and see if we've got some discretionary funds where we can pay for that, because it would be nice if we could waive that for you. But you register for this thing, and then after September 30th, I think sometime in October, they give you the prompt, which is, this is the system you're going to model, and here is the problem, the operational problem. It's usually a real system, like a real company that has given them a real problem with real data, and then you have to sort of come up with a real solution for that. And if you're selected to be one of the finalists, you will then fly to a professional conference to present your results, and then they'll decide which of the finalists go into first, second, and third. So there's a $5,000 price, unless they've increased this. When I first made the slide, was $5,000 for first, $2,500 for second, and $1,500 for third. So there's some cash value there. If you're interested, there's other competitions. So IISC also partnered with Flexsim. Flexsim is not a tool that we will use in this class, but it is another discrete event system simulation tool. It's very similar. And if you're really interested in this, I could also consider making this your final project, although you'll have to learn the Flexsim on your own. But this is focused on healthcare. And so it's a similar thing. You register, and then they give you a prompt, and the prompt will be an operational research problem that is meant to be solved with discrete event system simulation focused on healthcare. And there are additional, so Simio, which is another DES tool that actually kind of came out of Arena. The people who made Arena sold Arena, then they started Simio, and so it's very similar, and they have their own annual competition as well. So if you're interested in this, these are options you could do for your final project. Otherwise, you'll pick a system, usually a system on campus or near campus, take data from it, and model it using the tools here. And everybody, regardless of whether you do this or you do your own, will present at the end of the semester. Any questions about that? Thinking forward, in the next couple of lectures, I'll have duplicates of these just to remind people, because there's that registration deadline coming up. Yeah.
On the final project, are we assigned teams or we pick?
You'll pick, but they got to be within your lab section because you present within your lab section. And so nominally, there's going to be 4-person teams, but depending on how many are in your lab section and the timing of things, I basically run a linear program that tells me sort of what's the optimal number of 3-person teams I can get, or what's the highest number of 3-person teams I can get and still finish in time. And then that will give me a constraint, which I'll then let the TAs know. And so then when you come out to us, you say, I'd really like to be in a 3-person team, then we can check to see if that's allowable. So nominally 4-person teams, but potentially 3-person. And just due to scheduling logistics, we like to keep it inside your lab section, except in like really rare cases where, but then it gets awkward because if somebody's not in the lab section, I can't require them to come to another lab section. So that's why we keep it all over. Other questions? All right, so where have we been going so far? We've talked about DES simulation. They're very process-centric. What that means is if we're modeling an intersection like this one or a crosswalk, as some people do in their final project, you've got multiple processes that are generating entities that are competing for shared resources. So there's cars on roads, but there's also bikes on roads, but the bikes are also on bike paths. And then there are pedestrians on sidewalks. But, you know, the crosswalk is something that maybe they all share, even if maybe the bikes shouldn't be on a crosswalk, I don't know. But each process proceeds according to well-understood patterns. You know how cars drive on roads, you know how bikes do it, etc. Where things get interesting is when they compete for these shared resources and have to wait on each other. So our goal as engineers is to try to design these systems to prevent a lot of unnecessary competition, or to try to schedule them so that even though they have to use the same resource, they maybe are less likely to have to use it at the same time. So entities from multiple process can compete for these resources like a crosswalk. Activities are the times in which we view them to take on that resource. So it takes a certain amount of time for a person to cross a crosswalk. When you design an infrastructure system, you count on crosswalks, a person taking a certain amount of time to enter and leave a crosswalk, and you design traffic rules based on that. If you instead have a skateboard or a biker going across a crosswalk, the reason why that's dangerous is that the infrastructure was built under the assumptions that the entity will take a certain amount of time, and now they can go much quicker. And so it's these sorts of things. Similarly with, that's why there's certain pedestrian rules which formally don't apply to motor vehicles like bikes and skateboards, because their activity time comes from a totally different distribution. So the design is all off. So activities are how long it takes for you to use the resource. How long can you clear the crosswalk? A car clears the crosswalk much quicker because it's a thinner crosswalk and the car goes much faster. So that's what we're doing when we're modeling these activities. And then what we get out of that is the delays, which are the time it takes for the average time that everyone has to wait to get access to their resources. We don't know those ahead of time. That's why they're delays. So if I were to generalize that, we often use just when we start here, these MM1 models. If you're not familiar with Kindle's notation yet from 470, basically I'm just saying a single arrival process, a single server, and there's a queue of arrivals that wait when the server is busy. And I often can then characterize the service time, so the average activity, so the average time it takes to do this service, as some parameter, say mu, and the rate out of that might be 1 over mu or something like that. So you can characterize these in terms of rates or averages. And then I can also have an average arrival rate or an average time between arrivals. And so this is sort of one way that we kind of often start just to think about this process. And so we have entities that come into the system. We have resources like the server, which they all are trying to use. There's one server, it's limited quantity, that's what makes it a resource, and that's why they have to wait for it. So resources perform activities, and activities are the things that actually take time. If this activity was 0 seconds, then there wouldn't be any queuing, and this wouldn't be an interesting problem, because you'd come in and you'd immediately go right out. It's the fact that this takes an amount of time, and we know ahead of time it's going to take a certain amount of time, that makes this system interesting. And delays occur because of the misalignment of activities. What I mean by that is waiting for the next arrival is one activity, waiting for the service to finish is another activity. If I'm lucky, then the service will finish just as someone arrives, and I won't ever have anyone waiting. But I'm usually not going to get lucky like that. And so in these discrete event system simulations, we try to generate realistic arrival, inter-arrival intervals, and realistic service intervals that are necessarily not going to line up perfectly. And that's what's going to generate the delays. And so our goal as operations researchers and operations engineers is to try to come up with a new structure for how the system works, to try to make it so it's more likely that we can align the activities so that we don't get this delay as one activity is waiting for the other activity to finish. So, what is an entity, a resource, or an activity? I'm giving you these quick examples here. So it's all kind of determined by your research question, your question of interest. Your boss comes to you. Let's say you work for a logistics company, a global international logistics company, and they ask, on average, how long does each container on a container ship take to reach its destination? So what do you think the entities are that you should model in your model to answer this question? Containers, right? So containers are probably the entity. Why are containers the entity?
Because you're concerned about the state in which they are in the system.
I'm focused on the containers, and also the containers are these anonymous things that show up, they get delayed, and then they leave. And I'm interested in the generic container, how long does it take? So if I think about this here, containers are flowing through the system, and they're delayed by ships that can carry them. So in my inventory of ships, I have a limited number of ships or shipping routes, and those ships, the limitations on those ships are what are generating the delays of the containers. So the containers are my entities, and that allows me to track them. So I can stamp them with an arrival rate. I can stamp them with whatever time that they actually reach their destination. I can see how long it took. The ships are being reused with multiple containers, and so these ships are resources that are networked into shipping routes, and that allows me to, my operations might be to try different shipping routes. And if I try different shipping routes, maybe my resources will be more available so that my entities don't have to wait as long. And then ports aren't even modeled here. The action that goes on at ports, loading containers onto the ship and those sorts of things, are just abstracted away into a distribution of service times. We just say, all right, we need to load the container onto the ship. How long does that take? On average, it takes, 15 minutes to load a container, to get the crane out, to move it over, to pick the container up, and to drop it off on the ship. And so I don't have to model the port itself. I just need to know that on average, it takes about 15 minutes for the container to get there. Or this is the distribution. Sometimes it takes a half hour. It rarely takes less than 14 minutes, and I have some distribution. So that's, for this problem, this would be a good way to model. But we might have a slightly different problem. What is the longest duration a ship will stay at one port while loading and unloading? So now I'm not interested in the containers exactly, or if I am, it's in a slightly different way. Here I'm focused on these ships as the things that are coming and going, and I want to know what delays the ships. Now that ships are the things that are sort of, I'm not worried about the limited number of ships. I'm assuming I have as many ships as I want, how long is a single ship delay? So the ships are now an entity, and maybe containers are also an entity because maybe they both have to arrive together in order for the ship to be ready to depart. The ports are now a resource that it takes a certain amount of time for the port to load everything up onto the ship and for the ship to get out of there so the next ship can come in. And the loading of each container might be, again, an activity performed by the port. And so we don't have to model the cranes or anything like that, just so long as we have a good time handle on how long these things take. So then a third question I might have is, will opening a new canal increase the total number of ships unloading at ports? Well, here, again, I'm focused on the ships, but I probably don't care that much about the containers because I'm not really focused on loading and unloading. So ships are still my entities, but now ports and canals might be two different types of resources. How long do you stay at a port? And that delays how quickly you take on a shipping route. And then once you're on that shipping route, whether a canal is available for you to get through is another important resource. So the canals become the resource. And now that the canals are the focal resource, the activity is the time it takes to get through the canal. So how long does it take for the ship when it goes to the canal to get positioned in the right place and for the locks to engage and all of that so that you can actually get through the canal. So depending on the question, I might have different ways to model what appear to be the same system. So let your question drive your choice of entities, ports, or entities, resources, and activities. In the homework, I've kind of left it open-ended. I haven't given you a research question. So that's why it's just kind of an idle exercise. But when you actually go out and do your final project, you'll actually say, you know, I'm at this Starbucks and I'm really focused on this particular aspect of the operations. In order for me to model that, what do I view as my, like you might be focused on the customers coming and going, but you might also be interested in something to do with how long each barista, you know, works in a day and how long they have to work in a day, and maybe the baristas become your entities at that point. So it's really let your question drive your model. All right. Are there questions about that symptom? Yeah. Yeah.
Would there be any like actual reason to model the system with the distribution being
Well, so the idea here, the reason we go into the model is if we think that multiple ships competing for a resource will affect the amount of time the other ships will have to wait. So for one single ship in one single resource, there's no reason to do a simulation because the resource is going to be free, the ship's going to come up to the port or the canal, and it's just going to take that amount of time. But if there's 50 ships, and now one of them is stuck in the resource, the other 49 ships effectively have no resource until that ship goes through. So in this question, the question is, should we like add more ports or add more canals, those sorts of things. So given that we already have the Panama Canal, do we need to widen the Panama Canal? And so we could then say, well, right now the operation of the Panama Canal seems fine, but we forecast that in the future ships are going to arrive at the Panama Canal much faster than they do now, or maybe those ships are going to be much larger or something like that. So then we test a hypothetical scenario, a what if sort of scenario. We're saying, well, what if we had twice the number of ships? Well, now let's see what the average delay is. It might be that things get a little worse, but they're not that much worse than they are today. So it's not worth the extra investment of widening or adding a canal. But it might be that through our simulation, we find out that there's going to be massive backlogs at trying to get through these canals, in which case now we can justify putting in the money to build a new canal. Does that answer your question? Any other questions? All right, so you know, the other thing about entities that we focused on last time is that most of the time the entities are the things moving through your model. Had a car wash example where the entity came in, the entity departed. We had several examples where customers wait in line for servers or clerks. So they often move in the model. They always move in the model. Often they're moving in the real system. So we often view them in this general framework where the entity is mobile and the server is sitting in one place. But there are other cases, and I gave this kind of cute example of a vacuum cleaner, where the vacuum cleaner is a limited resource. There's only one of them, and it's moving. But it's randomly encountering things as it moves. And so it's really the entities that we're interested in, like how long until this region of the floor gets clean? How long does it take for this region to get dirty, and how do I adjust my operational schedule, the vacuum cleaner, to keep it clean within certain parameters? Well, the arrivals of dirt here and the arrivals of dirt to the vacuum cleaner, that dirt ends up becoming the entities, and the vacuum cleaner is like the limited resource. And we might want to buy another vacuum cleaner or whatever. So we can model that case by changing our reference frame, where we imagine sitting on top of the resource and allowing things to come to the resource. And then it turns it into something that looks like this MM1 example again, even though in the real system, the server is moving around while the people are sitting in place. You can imagine an emergency room that changed their operations where maybe they've got an ER doctor who walks around the emergency room as opposed to sitting in a room waiting for people to be brought to them. And that would be kind of another example. But the way you model it might be identical. You just might update your distributions for arrivals and service. Questions about the unit? Yeah.
Like in the previous example, there that entity would be the third part of the set.
I would say the entity would be the things that arrive at the vacuum cleaner, which would be generally junk that the vacuum cleaner has to make a decision about. It could be, types of dirt, water. It could be, I found a liquid spill. I found a large chunk of debris. I found a small chunk of debris. And the vacuum cleaner might make different decisions, whether it ignores a particular type or maybe it always takes on a certain type, those sorts of things. And we're trying to come up with that strategy, and the entities that are arriving are the different things we can make decisions about. Yeah.
This is going back a bit, but on the crosswalk example,
Yes.
Would the system ever simulate someone jaywalking or doing something like texting, driving, and hitting a pedestrian or something like that?
If you want to, that is up to you. I mean, that is definitely something we can study.
You can build it into the system.
Absolutely, right. So yeah, we might often just want to model, if everyone behaves, how would things work? But like I said, bikers and skateboarders and people on scooters often kind of, they don't necessarily follow our model rules for how things work. And then we have to say, well, all right, we need to model compliance in here. And so if 85% of the people on scooters behave according to, as if they're cars, that's fine. But these 15%, we need to inject them as these kind of other entities that are like fast pedestrians and then see what happens in the system. And that would be a great final project, is to sort of experiment with, accurately model an intersection on campus and play with compliance rates and suggest ways in which you could change compliance rates. As an example, the speed limit on the road, if you ask a civil engineer, that's the 85th percentile speed. Their goal is not for everyone to drive the speed limit. Their goal is to adjust enforcement so that the speed limit on the road represents the 85th percentile of the speed. So 15% of the speeds are actually above that because they know that people are going to violate that. So the goal is not to keep everyone under it. The goal is to adjust compliance so that there's only a certain number that are over that, and you can simulate that. Yeah?
Just out of curiosity, will entities ever be static, or do they have to be flowing?
Well, they're flowing through the model typically because they have to move. They have to be used by a resource, kicked out of a resource. But in the system, they can be static. They can be totally ignored. But in the model, they at least have to have the potential to move, or else they're just, they're maybe a part of the system. They're a constraint. Like this table isn't really an entity. I just have to move around it when I walk. But if this table starts moving on its own, I might need to model it differently.
Okay. And you said that resources are the ones that bring them in and then kick them out, right?
Resources that's just our generic term for anything that delays an entity for an amount of time that we can kind of predict it. So they are the limited thing in the system. Okay. All right, so then we went through this whole example. I'm not going to go through, again, I'll just sort of go, speed through with kind of the background narration that you learn these rules that allow you to go from one event to the next. And that actually allows you to pull yourself all the way through time. And this is what's going on in the simulation. Those rules being, initially you schedule your first arrival and you schedule the end of the simulation. And hopefully those of you who've done the lab and the homework are familiar with this already. And then you continually process scheduled events based on what comes next in the future event list. And so if you happen to get an arrival event, then typically with a system like this, the set of rules are going to look like this, where you move clock to that time. If the server's available, you move the entity into the server and you schedule the departure. Otherwise, you move the entity into a wait queue, and so you're done with that entity for now. You can't schedule anything because you don't know when it's going to enter the server. Then you schedule the next arrival, create an arrival at that schedule, and then if you have any statistics you need to generate, you update them. And you just do that for every single arrival event. You follow that logic, and you're guaranteed that if you follow the logic for the other things, that you will move through time properly. On departure events, there's similar logic. Move the clock forward to that time. If you've had a departure and the wait queue is not empty, you can now schedule a new departure because you can take something out of the wait queue and put it into the server. And then you can update and collect your statistics. You just do that on every departure event. And then if you're end event, you just move the clock forward to that event time, update and collect statistics, and terminate your simulation. In the book, and I'm happy with you doing this on your homework as well, in the lecture book, the Banks book, they don't even generate a new row for the end event. So once they're done processing the row before the end event, if they see the next event in the FEL is an end event, they just stop there. And that's totally fine to do. So whereas in the laboratory simulation, just the way it was structured, you end up sort of processing the end event on the very last row. But if for the homework, it's fine. If you want to create a row for the end event where nothing changes, where it just processes the end event, that's fine, but you don't have to. I'm fine if you just leave that extra row off. All right, so commonly used state variables in these types of systems, LS and LQ that we've talked about already, the instantaneous utilization, whether a server is busy or idle. So if you only have one server, it's only going to be 1 or 0, but as we saw in the lab example, if your server can go up to 30, then it'll be some fraction of 30. The related attributes that you might need to update are these arrival times. And so an entity comes in, you stamp it with its arrival time because you might need to use that later when you're calculating its response time. And then we've got these performance measures. So you might want to count the total number of parts that came out of your system. You might want to count the maximum waiting time. So over the set of all parts that were handled, which one had the maximum amount of time waiting in the system. You might want to average all of those and say, overall of parts, what was the average waiting time? So all these are sort of focused on the part perspective, but you can also take the time perspective. And I can say, well, if this queue is the number of parts in the queue at any instant of time, I can take the integral under that curve and divide by the total length of time in that interval, and that gives me the average number of parts waiting in the queue. So this is sort of a queue perspective where I'm integrating over time as opposed to number of parts. And I can take maxes over time intervals and averages over time intervals as well. And then utilization, which is what you used in the lab example here, where again you're taking the integral under the instantaneous utilization curve to give yourself an average utilization. So these are common things that you'll see in these examples over and over and over again. So common that Arena has them defined for you and ready to calculate without you doing any extra work. So that's why I'm introducing these to you, but you can come up with your own. Your stakeholder may decide that there's another performance measure they really care about, and you'll have to code that up yourself. All right, so what do you get from the output of these things? So if you imagine, let's say I had a server like this, and the what if question I'm interested in is what is the effect of doubling the arrival rate? What if I doubled the arrival rate? Well, as I hope you'll see when you're doing the lab case, the lab examples and the homework examples, depending on if you run these things over and over again, if you have different arrival schedules, you'll get different answers. So I might get, these are each box, you can't read this here, this is total production, this is plotted on this axis. So this is, I plotted, the circles that are on the top are a baseline arrival rate. The triangles on the bottom are the doubled arrival rate, or the performance measure in a system with a doubled arrival rate. And it's just plotting them horizontally. This is, I think, taken from your laboratory text. And so this is total production from 0 to 10, average waiting time in queue, average total time in system, and so on. So these are all different performance measures you could get out of that. And what I want you to take from this, and I've bolded in the first replicate. So that's the first replicate, that's the first replicate. But then you do another replicate, and you might get a totally different number. So you generate a bunch of replicates, and you get a spray of numbers in one condition and a spray of numbers in the other condition. If you just took a single replicate, you might think that it's clear that the triangles are going to have maybe a higher total production than the circles. But once I generate, say, 10 replicates of both, then now this spray overlaps with this spray, and it's really difficult to tell which one's better. Similarly down here, I happen to get, this is my first replicate, and this is my first replicate, but what if my first replicate happened to just come out to be this one in the triangle case? And that way, I would make the wrong inference if I only use the one replication. So because I have variation in my inputs, I'm going to have variation in my outputs. And so the effect is not going to be clear without taking a statistical approach. And so this is where things like 380 will come into play and more sophisticated statistics. So, you know, I might want to look at, say, average waiting time in the queue, and I want to test the hypothesis that the average waiting time in the queue is more or less in one case or the other. So if I double my arrival rate, I might want to test the hypothesis that the average waiting time in the queue is higher in the double case than in the normal, the baseline case. Well, I know I have a way to do that, a t-test. So a t-test provides me a way that if I get a bunch of data here and a bunch of data here, the t-test will test the hypothesis that the two averages are the same. So that's where those tests, those hypothesis tests that you've been learning are going to come into play. Is that we'll talk about those and others that you haven't learned yet that allow us to look at these data and make a conclusion that isn't just based on a single shot or a single average, that takes into account the variation. So that's where we're going, and that's the stats part of this will primarily be after the midterm. All right. So any questions? Yeah.
Is B of T always going to be either 0 or 1? Can it be like, for example, like a rate of utilization rate?
Well, B of T, usually instantaneous utilization is a snapshot of how many resources are used now. So it's never a rate. But it doesn't have to be 0 or 1. It can be something in between 0 and 1. So if I have 30 resources, then it might be 5 out of 30 or 6 out of 30. But it's not going to be. If you could probably come up with some utilization rate that would be a different metric, but you would sort of be measuring something different. So if you're measuring utilization, it's never in per unit time. It's always in like, what is the utilization now? You could ask, how does the utilization change over time? Like, you might be interested in how it decays. Like, if I take away all the customers, how quickly are my servers going to go idle? That might be an interesting utilization rate. All right, so let's then do this hand simulation here. So skip over that attendance exercise. We'll do another one later, so everyone's seen what you're supposed to be doing in the homework. So the homework starts out, it looks a little bit like this up here. I generated new numbers, new inter-arrival times, and new service times here, but otherwise this is identical to what you're doing in the homework. I'm not going to list all of the performance metrics that you calculate, but hopefully you get kind of the picture here. So the inter-arrival times, when I say that, I mean that each one of these numbers represents a waiting time between customers. In reality, they'll be real numbers. Here we're just making them integers to make the math easy. But when you do this for real in a real simulation, then these are just drawn from a distribution that could be anything from 0 to infinity. So an exponential distribution is often used for the simple cases of inter-arrival times. And then service times, each one of these are the times required to serve a customer once the customer gets there to service. So one way you can view this is maybe customer 2 has a more complicated request, and that's why they need more service. Where customer 3 maybe just needs to drop something off and pick up a receipt, and that's why they need less service. Or there's just variation. Maybe the clerk is having a bad day. And so, this particular time the clerk takes longer, and this time is shorter. So there's variation here, and I've just given you random numbers here, but when you end up doing this as we move on in the course, we'll actually end up focusing on rates or averages and then draw from distributions so that when you need a new inter-arrival time, you just ask the distribution for one, so you don't know the list ahead of time. For now, I'm giving you the list ahead of time. On a midterm, I'll probably give you the list ahead of time because I don't need you to be drawing random numbers from a calculator or something. In reality, when you do these sims, when you're off, at an internship or a job, then you actually draw them from a random distribution. And you'll start seeing how that works in Lab 3. Okay, so the first customer has no inter-arrival time because we start the simulation right when she arrives. So there's nothing before her, so I'm interpreting this table as how much time do I wait for customer 2 after customer 1 arrives. And that's why it's sort of written this way. So are there questions about the format of this table? Already I think we had a discussion post where someone asked about this empty space, which is the common question to ask, and I know a lot of people have that question. Any questions about interpretation? All right, so state variables, what to worry about. So the book just uses LQ and LS. Sometimes you might see NQ and NS. This is the number of customers in waiting for service and the number of customers currently being served. For this type of system, only one customer can be served at a time. So LS is always either 0 or 1, but LQ could be infinite. But it could be as low as 0. Our cumulative statistics, I kind of already went over these. The number of customers who have departed by this time, the total response time for all customers who have departed by this time. And so the response time includes the total time from the customer's arrival to their departure. For each customer, you subtract those two numbers and you add that to this total response time, S. And then there's this F that's in the book that we won't calculate here, which is the total number of customers who have departed whose response time is 5 or greater. So whereas here you always add 1 on a departure, in F you only add 1 if the response time is 5 or greater. Are there questions about any of these definitions? And all these they also go over in the book. Okay. So the entities here are the customers. Customers have 2 attributes. Their ID, which just differentiates between customers. It's not that important. So your customer 1 through 5. And their arrival time. We have to stamp them with arrival time in order to calculate the response time. If we didn't have an arrival time attribute, when they would leave, the only way we could figure out how long they've been there is by looking up through the simulation table. So instead of having to search through the simulation table, we just want to create, this is effectively like, I don't want to call it a state variable, but this allows us to only kind of focus on the current row as opposed to trying to look up the rows to figure out what the arrival time was. So this makes it more convenient to calculate response time. And so this down here, C1, 0, that means customer, that's the C. ID, that's the first number, and arrival time, that's the second number. That's how we interpret that. Then we've got this waiting and service area, which is a checkout line, which is a state variable that queues up customers. And so our checkout line is always going to look, it's either going to be empty or it's going to look like this. The customer on the far left is the customer being serviced. If there's anyone in the checkout line, the person on the far left is the one being serviced. The server will only be idle if the checkout line is empty. The others, all of the others, are waiting for service. So the number in service is going to be 0 or 1, which basically is going to be 1 if anybody's here. And then the number in the queue is going to be the number of customers, it's basically the number of customers in the checkout line minus 1. So LQ plus LS will always add up to the number of customers in the checkout line. So as we move through, we update both LQ plus LS as well as the checkout line. All right. Then the 3 types of events that we have to worry about. The end event, which is just when the simulation ends. We sort of schedule that arbitrarily. The arrival event and the departure event. The way we interpret an arrival event, A, T, CI, is that customer I arrived at time T, or will arrive at time T. Departure, customer I will depart at time T. And those get put into an event calendar, or as the book calls it, a future event list, FEL. And it looks like this. It's going to look a little like the checkout line. And so the first event in the FEL represents the event you'll process in the next line of the simulation. And then all the other events are just events that you'll eventually process so long as they are before the end event. Make sure that your future event list is kept in time order so that the first event on the list is always the next thing you'll process. So notice this is 11, 15, 16. You'll schedule these things out of order. So you might have known that you were going to have this departure before you had this arrival. And so when you schedule the arrival, it would be tempting to put the arrival here or over here. But you always want to make sure the FEL is ordered. Any questions about any of this so far? Yeah.
What was it, D again?
D is departure.
Okay.
There will be customer 3 will depart at time 11 in the future. So on arrival, and so we'll actually do lines of the sim in a second, but this is the logic that we use. Someone arrives. If the checkout line is empty, then that means they can go directly into service. So we schedule their departure immediately, and that's just going to be scheduling at whatever the current time is, plus whatever service time is associated with that customer. And then we increase the number of customers being served. Otherwise, if the checkout line is not empty, this customer has to wait. So all we do is we increase the number of customers that are waiting. Of course, in either case, we add them to the checkout line. So we always add them to the checkout line. And now we're done processing arrivals. When you're done processing an arrival, inter-arrival durations are activities. When you're done with one activity, you have to schedule the next. So when you're done with one arrival, you have to schedule the next arrival, or else it won't ever happen. So we're done with this arrival, so we remove it from the future event list, and then we ask, what's the next inter-arrival time? We add it to the current time, and then we schedule the next arrival of the next customer. We add that to the future event list, and then we use the future event list to figure out what happens next. If we happen to have got a departure event on our future event list, instead, we increment the number who departed. We add the response time, which is just the current time minus the arrival time of that customer, which we know by looking at their record that's stored in the checkout line. And then we remove them from the checkout line and subtract one from the server. There's now no one's being serviced. But that is then going to allow us to schedule the next customer if the checkout line still has customers in it. So then we'll re-increment that LS if there's another customer waiting. We'll decrement the LQ because now we've removed the customer from the queue, and we'll schedule that new customer's departure. And then we'll move on, and then eventually we'll hit an end. And if we just hit this end, we terminate the simulation, and we might do any cleanup logic. Now I'm going to, as we go through this here, which is very similar to what we'll do on the homework, I have this little timeline down here just to keep track of where we are. You don't need to do that on your homework. You don't need to show any timeline. All we're looking for is the table, but your table, I think, also has the F in it as well. So we simulate for 15 time units. That tells us the end time. So the first thing we do is we schedule the end of the simulation. So in yours, I think it might be 30 or 40. So you'll schedule an end event, and you can for this first line, I'm going to build it up piece by piece, but for all other lines, we're just going to knock out the whole line in one. So I might, as I'm writing this down, write E15 in pencil, or if I'm using Word, I just type it in so I can move it around, and because I know that event is coming up. The next thing I need to do is schedule you can think of it as sort of scheduling your first arrival, but in this case here, you can kind of think of it being scheduled before the sim. Now you're processing the first arrival. So this whole line is effectively you processing the arrival of customer 1. So what do we do on an arrival? Well, I'm going to set the clock to the time of the arrival. I am then going to schedule the departure because I see that the server is currently not busy. So LQ plus LS is equal to 0. So I can schedule the departure. Where do I get that departure? Well, customer 1 up here spends one unit of time in the server. So I just take 0 plus 1, and that is where I get the 1 in this departure. So then I increment my server from 0 to 1, and then I add customer 1 to the checkout line. And I know that whoever's first in the checkout line is currently being served. And then I have to then schedule customer 2. Well, if I look up here, customer 2 arrives 4 time units after customer 1. So I just look at the current time, and I add 4, and that gives me this arrival event here. And that's basically all I need to do for that first arrival. So I'm filling in the rest here, or I just pulled LQ down, because it didn't change. These start at 0, and I'm done with that arrival. So my next step will be processing this departure. But before I do that, are there any questions about just that far?
Are you
I just gave it to you. I said, we're arbitrarily going to simulate for 15 minutes. It's like you saying that I really only care about this simulation for a work day, so I'm going to end the simulation at 5 p.m. Now, you can have other stop conditions, like I want to simulate this until I get 100 customers. But we're just going to start out simulating for a fixed unit of time, and I'll give you that unit of time. Yeah, question in the back. I don't think I'm confident enough to say that it'll always look that way, because what could potentially happen is, like, we were lucky, I guess, here that this departure event happened to happen before this arrival. But if the service time here, instead of being 1, imagine that service time was 9. Then in that case, the departure of customer 1 wouldn't have happened until 9. And in which case, the next thing to happen wouldn't be a departure, it would be an arrival. And that arrival, in some ways, customer 2 is lucky because customer 1 is going to be cleared out of there before customer 2 arrives. But if customer 1 took a long time, then customer 2 is going to have to wait. So the order in the future event list, you can't really know ahead of time. It depends upon how long the service times are going to be and what the inter-arrival times are. Does that make sense? But it will, in most of your FELs, you're always going to have an arrival. The only time you wouldn't have a departure is if the checkout line is empty. So you're always going to have an arrival and an exit. And the thing is, the exit is not necessarily the last event. You can schedule things after the end, but you just won't process them. All right, so let's move on to now we process the departure. So we're going to jump to the departure event. So the first thing we do is say, well, what's the current time? Well, so somebody's departed. So the order in which we do these things sometimes can vary. We increase. We're going to have 1 departed now. So that will end up showing up here once I'm done refreshing this whole line. We've now, because we've had a departure, we keep track of how long customer 1 was in the system. Customer 1 arrived at 0, and she departed at 1. So she spent 1 unit of time in the system. So I'm going to add that to the accumulating S here. I'm going to remove customer 1 from the checkout line. And then I'm going to decrease the number being served down to 0. So after all of that, I jump to my next clock here, and I see I'm at clock 1. Both of these are 0. There's nobody in the checkout line, which means the server is now idle. And the server will be idle until the next event, which is an arrival. And so here are these 2 stats here. So S got incremented to 1, and ND got incremented to 1 as well. All right, so the next step there is I need to process the arrival. And so I now have to do an arrival just like in time 0, but now I'm doing it for customer 2. So again, I got an arrival and the checkout line was empty. So if I go back to my rules, I say if I get an arrival and there's nobody in front of me, I go directly into the server. Whenever I go directly into the server, I can schedule when I get out of the server because I know the distribution of time it takes to get through service. So I can schedule my departure, and I just look up here, and I see that customer 2 takes 8 time units, but she arrived at time unit 4. So that's our current value of the clock is going to be 4. So 4 plus 8 gives me the departure of 12. So customer 2 is going to depart at 12. I'm going to then add her to the number being served at this time unit. I'm going to add her to the checkout line. And now the last thing I need to do is schedule the next arrival, or else the arrivals will never happen. So I look up at the table, I see customer 3 arrives 2 units after customer 2. So I schedule her arrival to be 4 plus 2, and I can add that to the list up here, and then I'm done with clock 4. And so now I've got all this updated here, and notice that I skipped, even though I only skipped 1 minute here, I skipped 3 minutes here. So that's how these DES systems things work, is they're these irregular time jumps, and we can ignore everything that happened between 1 and 4 because we're only focused on these events. Question?
So if you had someone leaving and then arriving at the exact same time period, is that just processing as one time jump? Just like
yes.
Instant, one goes in, one goes out.
Right. I mean, so typically what you do is you compress them all into one line. There are some people that will split them out, so you'll see like 0, 1, 4, 4, 4, 4, 5 or something like that. And so, but but then the ordering of these things gets a little funny. So I just say accumulate all those effects into one, but just be careful about it, because sometimes like it's easy to forget to do something when you're processing multiple of these things at a time, or duplicate. Like you might end up scheduling multiple arrivals or something like that. But I would say for this exercise, I don't think we have anything happening simultaneously, but if we do, process them all so that your clock only has one time unit. Yeah, question in the back? Customer 2 arrived at time 4, right here, yes. Why does the clock, I'm sorry, I missed that, so the clock is 4 when, so customer 2 arrived at time 4, and now I'm down here, this is clock 4 and the time here. So customer 2 arrived at time 4, got added to the checkout line, and won't depart until 12. So she still is arriving at 2. Is that clear, or did I? So, what? Oh, so I see. Okay. This column here is the list of things that have not happened yet. So at time 1, we have these number of events that we know will happen but have not happened. That's why it's the future events. Question.
So, your event list, are you going to process all of the events, like, but the exit, like the end of the simulations?
You will end up processing everything that happens before, like, so if I were to keep going through this, as I can do here, eventually what I see is I do end up getting arrivals and departures that are actually scheduled after the end of it. But what's going to happen is that when I'm in clock 13, when I jump to clock 15, and I basically just ignore these other events. I don't even schedule another row there. So you can have things after the end.
So, but how like processing an end of simulation look like?
So okay, so that's right here. So we at this point I have just done clock equal to 13, and so my next step is I say, well, what's first in the future event list? And I say, oh, the end event is first in the future event list. So for this simulation, there's nothing special we have to do at the end, so we just stop. In other simulations, there might be some other calculations. As an example, let's say, like in the lab, I might be interested in the average response time per customer. So in my end event, that tells me that I should generate that aggregate stat, where I divide this number by this number. So 16 by 3, kind of like you do at the very end of the hand simulation in your lab exercise. So that might be kind of viewed as end event logic. But there's really nothing you do at the end. You don't have to add another row for the end. You only are interested in all rows before the end of it. Any other questions? So I could have gone through all of those, but if I look through this, if I go back through interesting things that happen here, maybe I can focus on. So clock 4, we had that. The next event after clock 4 was the arrival of customer 3. So customer 3 arrives. So that's right here. So now customer 3 arrives, but customer 3 is not going to be able to enter service. And so this is an example of when I have an arrival, I don't schedule the departure, because the arrival, I have no idea. I mean, yeah, you can look ahead and kind of think about, I know that customer 3 is going to start at time 12, but don't do that. Resist the temptation of forward simulating in your head. Let the paper, let the computer simulate. As far as the computer is concerned, it can't see anything but the first item on the future event list. And so we have no idea when customer 2 will end service. So we have no idea when customer 3 will end service, because we don't know when customer 3 will start service. So when customer 3 arrives, all we can do is add her to the queue. So that'll be incrementing LQ and adding her to the checkout line, and then scheduling the next arrival of customer 4. And then we're done. And so that in that particular case, the future event list looks very similar to the previous one. It has the same departure, the same end, and a different arrival. But now there's an additional, now customer 3 is waiting. So that's an example of how you process the arrivals depending on the state of the system. Any questions about that? So, so again, the F here, if we were to calculate this, so right here, when customer 3 departed, she actually had a service time. So customer 3 arrived at 6, she departed at 13, or will depart at 13. So when she departs at time 13, if I had an F column, I would have added 1 to F, because she is one of the ones that had the unfortunate case of having to wait a long amount of time to get in and out of the system. But I might have a bunch of zeros in the F's up here because all of these got out pretty quickly. All right, well, if you have any other questions, feel free to let me know or email on the discussion board. It's great that you guys are using the discussion board because I can post responses to everybody. The attendance exercise for today. So let's do the question of how many arrivals should be in your homework's future event list in every line. So I said there's a sanity check where if you did it correctly, your future event list should have a certain number of arrivals in every line. So what was that number? And otherwise, that's all I have for you.